Here's section 3.3, and we're looking at our definition of linear dependence and independence. Okay, there we go. For dependence, linear dependence, what we have is a set of vectors x1, x2 up to xm in I'm going to go with Rn. They use an F for any field, but typically for us, we're working in the real numbers, are linearly dependent if there exist scalars, C1 up to Cm, such that, oh, well, I forgot the most important part there. Not all 0. Okay, so some could be 0, that would be fine, but not all can be 0, such that C1 x1 plus C2 x2 plus all the way to Cm xm is equal to the 0 vector. Okay, now so there are various ways to look at this, and I don't they don't really get to matrices for a while in here, but just to kind of point out what's happened is, right, I've got these this linear combination of, if I make these column vectors, what I could do is, I'm going to use an A here instead of an X, but if I make the matrix x1, x2, x3, now up to xm, so I really don't like the m there, but the n makes sense for Rn, and so we're stuck with it for now. So if I let A equal that and C equal C1, C2 down to Cm, like that, you see what this is saying is, if I can take the columns of matrix A and take A times C, get 0, right? If so, A times C equals 0 if there is a non-trivial solution to this, then you know, x1, x2 up to xm are dependent. Okay, so you can think of it this way with, you know, our linear combination of the vectors, or you can think of it as columns of a matrix. So I have columns of a matrix, and I'm looking to see if there is a non-trivial solution to a homogeneous equation. Okay, and if there is a non-trivial solution, that non-trivial solution would have at least one of those C's be non-zero. Then it says those columns of A were dependent, and it's, you know, it's saying the same thing as up here, that not all of those C's are zero. Okay, so that's dependence, and then independence is if C1 x1 plus C2 x2 all the way to our Cm xm equals 0 implies C1 equals C2 equals all the way to Cm equals 0. Oops, not a vector 0, just 0. If those are all, if this being true implies that all those coefficients were 0, then the xi are independent or linearly independent. Now again, in terms of a matrix, it says if, you know, AC equals 0 only has the trivial solution, then the columns of A, which we had made up there as, you know, our x1, x2 up to x sub m, are independent. So looking at it as columns of a matrix or just standalone vectors, you know, so if you take, you know, here's an example. If you take something like, oops, your x1 is equal to 1, 1, and x2 is equal to 2, 2. Then, you know, notice I could take -2 times x1 plus 1 times x2. Okay, that would be -2 times, it's a terrible -2. -2 times 1, 1 plus our 2, 2, and that's -2, -2 plus 2, 2, and that is the 0 vector. Okay, or, well, you know, do a little better than that. I guess I could go -2 plus 2 minus 2 plus 2, which gives me then the 0, 0, which is the 0 vector. Okay. So that gives me the 0 vector, and certainly those were not zeros. Okay, but you know, similarly, right, I could have looked at this as this matrix 1, 1, 2, 2, and times what was it? -2 and 1. So -2, 1. All right, so there's my vector A, there's my vector C, and when I do this, I'll get my -2 plus 2 and a -2 plus 2, which is 0, 0, which is the 0 vector. And so there's my non-trivial solution to that matrix equation. See, so I can think of this sort of either way. I can think of it as, you know, this sort of you know, linear combination structure that I see up here, but I can also think of it as putting my columns into a vector and asking, is there a non-trivial solution to the homogeneous equation? Okay, so there's an example of dependence. You know, an example of independence is, you know, suppose I have these, x1 equals, say 1, 1, 0, and x2 is equal to 0, 1, 1, then the only way I'm going to get 0 out of this thing, right? So let me erase that. Now, so if I'm looking for, you know, C1 times 1, 1, 0 plus C2 times 0, 1, 1, you know, that is going to be the vector C1 and C1 plus C2, and then C2. And now if I say that is equal to 0, 0, 0, the 0 vector, right, the only way that's going to happen is you look at the C1 and the C2 is if C1 and C2 are 0. Okay, so that's the only way I can make this work, is to have C1 and C2 be 0, and therefore they're independent. Okay, so x1 and x2 are independent. Again, you know, if I do this as the matrix situation, I have 1, 1, 0, 0, 1, 1, and I'd like to multiply that times, you know, some C1, C2 to get 0, 0, 0. Well, I guess I can set up a, you know, an augmented matrix, right? And so to look for a solution, I'll do a solid line there, 0, 0, 0, 1, 0, 1, 1. And if I subtract the top row from the middle row and replace the middle row, I get 1, 0, 0, 0, 1, 0, and 0, 1, 0. And now subtract the middle row from the bottom row and replace the bottom row, and my new one is 1 0 0 0 1 0 and 0 0 0. Okay, and right there that says, all right, that implies C1 equals 0, C2 equals 0. Those are my only answers. So again, I see independence that way. So that's the idea of linear dependence and independence. And again, you can think of that as these individual vectors, but you can also think of those individual vectors as columns of a matrix. Okay, so there we go.